The last of the big conservation laws that we're going to deal with this semester is the conservation of angular momentum. And to set up conservation of angular momentum, let's start by going back and looking at the conservation of linear momentum, because what we'll see is fundamentally what underlies the conservation of linear momentum is very similar to what underlies the conservation of angular momentum. The conservation of linear momentum comes straight out the translational version of Newton's second law. So thinking about how Newton's second law applies to a system of objects. And so what we've got here is an equation that tells us that the net force acting on our system is equal to the change in the linear momentum of our system with respect to time. And so all we're going to do is just rearrange this equation. So take the delta t over to the other side, and then I know I can break up the net force acting on my system into two pieces. So the sum of the internal forces plus the sum of the external forces acting on the system. And from Newton's third law, I know that the internal forces, when I add them up over the whole system, those disappear. So what I get here is that the change in the linear momentum of my system is equal to the net external force acting on my system times however long I let that force act. All I want to do at this point is make two notational changes. The first is I'm going to break apart this delta p term. So this is final minus initial in terms of linear momentum. And so I'm going to take the initial linear momentum over to the other side. And so what I get is this expression that tells me that the initial linear momentum of my system plus the net external force acting on my system times a chunk of time is equal to the final linear momentum of my system. The last notational change I'm going to make is just emphasizing that, well, how do you get the initial and final total linear momentum of your systems? You simply add up all of the initial and final linear momentum vectors. So this last little notational change is again just emphasizing that this is a vector addition problem where I'm adding up linear momentum vectors to get the initial linear momentum of my system. I'm adding up linear momentum vectors to get the final linear momentum of my system. Well, this equation should look familiar because its form is very similar to our conservation of energy or energy balance equation. You can think of this as our linear momentum balance equation because fundamentally what it's telling you is that the total initial linear momentum of your system plus how you change that momentum by letting some net external force act on your system over some chunk of time is equal to the total final linear momentum of your system. So this equation tells you how the net external force acts on your system over a period of time to change your system's linear momentum. So what are the important details we need to remember when thinking about this equation? Well, the first is basically what we just said, that this equation tells us how you change the linear momentum of a system, and it's with this term right here. And we gave that term a name. We said that that was the net external impulse acting on the system. If you have a net external impulse that acts on your system, then the linear momentum of your system changes. Well, this also tells us under what conditions the linear momentum of our system is conserved. So if you make that net external impulse zero, then that means this term goes away and you're simply left with the total initial linear momentum is equal to the total final linear momentum. That's conservation of linear momentum. So what are the conditions under which this net external impulse term disappears? Well, one is if the net external force is zero. If there's no net external force, then it can't cause a net external impulse. The other is if the time you let that force act is effectively zero. So this is what happened with collisions, where with collisions we said even in situations where there were net external forces acting on the system, the magnitude of those forces was much smaller than the force that one part of the system would exert on the other. And the time that that collision happened was small enough that we could effectively treat the net external impulse as zero. The third thing this equation was telling us is that this is a vector problem. So again, what we're going to do is we're going to break this equation up into components. So if you have all your linear momentum vectors lie along the x-axis, you have a single equation. If they all lie along the y-axis, you have a single equation. If you have linear momentum for your system that points in both the x and y directions, then you need two equations to describe that. And so for both of these equations, we still have this condition that says if the x component of the net external impulse is 0, then the x component of the linear momentum is conserved. Similarly, if the y component of the net external impulse is 0, then the y component of the linear momentum. This is how we set up conservation of linear momentum. Conservation of angular momentum is very similar. It simply comes out of the rotational version of Newton's second law. So if we have some system, the rotational version of Newton's second law, when we apply it to our system, tells us that the net torque acting on our system is equal to the change in the angular momentum of our system with respect to time. And so again, we can play the same game we did before, where we multiply the delta t over, we think about the net torque acting on the system as the sum of internal torques plus the sum of external torques. The internal torques, again, that's just going to be the torque that one piece of our system exerts on another, and when we add those up over the whole system, those torques will disappear. The change in the angular momentum of our system is equal to the net external torque acting on my system times some chunk of time that I let that torque act. We're going to break up this delta term, take the initial over to the other side, and again what that gives us is an equation that tells us that the total angular momentum of our system initially plus the net external torque acting on the system times this chunk of time is equal to the final angular momentum of the system. We're going to make our same notational adjustment to again emphasize that you get the total initial and final angular momentum of the system by simply adding together the individual initial and final angular momentum vectors. And what we've got is another balance equation. So this is, you can think of as an angular momentum balance equation. And again, it's telling you that how a net external torque acts on your system over a period of time will tell you how you change the angular momentum of the system. So what are the important details with this equation? The first one again is that this equation tells you what causes the angular momentum of your system to change. It's the net external torque acting on your system over time. And you can think of this as the net external angular impulse. So it's absolutely analogous to the net impulse that we talked about with linear momentum. It is telling you how the net external torque acts on your system over time, and that will change the angular momentum of your system. Of course, that means that this equation is also telling us when the angular momentum of our system is going to be conserved, because that's going to be true exactly when the external angular impulse is 0. So if the external net torque does not exert an external angular impulse on the system, then that means that the angular momentum of your system will be conserved. So what are the conditions under which this is true? Well, there's no net external angular impulse if either the net external torque is 0, or again, you let the time that that net external torque can act be so small that it is effectively 0. So again, we'll see situations where now we're going to let things collide, and those collisions will generate angular momentum, and because those collisions occur over very brief chunks of time, we're going to be able to say that the angular momentum of our system is conserved during that collision. This equation is also a vector equation, with the one caveat that of course we're going to continue to work problems where our forces act on objects in the xy plane, which generate torques about the z, and so our conservation of angular momentum will happen about the z-axis. So we're going to have conservation of angular momentum problems where we're only conserving along a single dimension. So we're going to have a one-dimensional problem where we're going to say that the total angular momentum of our system is conserved. The one additional detail that we need to make sure we understand with this equation that we didn't have to worry about with linear momentum is that this equation cares about what choice you make for the pivot point. So what we really want to read this equation as saying is that the initial angular momentum of the system about some point O plus the external angular impulse exerted on the system about point O, so about that same point, is equal to the final angular momentum of the system about point O. So we simply have to remember when we're using this equation, we have to care about our choice of pivot point, and we have to keep that choice consistent over all the terms that we try and calculate out. So this lays out what we mean when we're talking about conservation of angular momentum and tells us when angular momentum should be conserved. What the next video is going to do, tell us how we work problems when angular momentum is conserved.